It's a great pleasure to be here again, and the discussions have been just fantastic. And I want to present to you today some work we actually did a couple of years ago, but we're still working on it. And it has amazing, I think, applications to all the Artemis sites. So this is a joint effort by international colleagues, in particular Lunar veterans, if you will. You may know that Sacha Basilevsky, the senior author here, was in the operations room. Long story there. Mikhail Malenkov has been worked really hard on all the details of the preparation and testing of the rover, and we have a lot of other people who are engaged and involved. Dave Scott, the Apollo 15 commander, Ron Creel, who has worked with the thermal aspects of the rovers, et cetera. Next slide, please. So we try to use all these data to look at Mons Malapert, which is like clearly a very high resolution target. Next, please. So we all know where it is, of course, and it's really important because geologically, the really critical thing is that it's apparently a massif from the South Polacan Basin. So that's good enough right there. But it also has the near constant illumination conditions and potentially water ice and cold traps for the regolith, two major craters just below Mons Malapert. Indeed, it's a key candidate for location of bases and activity, which gets us essentially information about the solar illumination, which can be had year round. So we investigated the topography, the geological and trafficability aspects of Mons Malapert. This is the paper here in Solar System Research that we published in 2019. Next slide, please. And I refer you to that one for details. So it's 5 kilometers above the 1838 datum, constant visibility, long periods of sunlight, 87 to 91% of the year. And this is clearly an important factor for electrical energy production. Okay, so you want to site your solar cells there, et cetera. And clearly you'd want to have not too long wires extending kilometers and kilometers away. So you probably want to have your outpost and your base there as well. So that's what motivated us to look at this and think about geologically, next slide, please, how, in fact, this could be utilized and what the problems might have been. So it's back up, yeah, 30 to 50 kilometers, elongated in a west-northwest direction. But the slopes are locally steep, up to 20 to 30 degrees. And this is really kind of important. A good thing is that Haworth and Shoemaker craters to the south of Mons Malapert, these are two 50-kilometer craters which show essentially a neutron spectrometer signatures suggesting significant water ice content. So obviously this is a great place because you could go to the south, get the water, et cetera, harvest that, come back to the base and the power station, et cetera, and press on. So how feasible is that? Well, this slide shows you the slopes. They're invisible at this resolution, but you can see the slopes are very steep coming up the sides and not so steep on the margins. Next, please. And a critical aspect to this is, in fact, that the summit and base are covered by numerous small craters. You can see in the top image and the bottom image. But the steep slopes show a distinct deficit of craters. It's not because the South Polacan Basin formed yesterday, okay? It's because, in fact, the slopes are steep and there's downslope movement of material. And in particular, it's not just any kind of downslope movement. There's this elephant hide terrain, which you're all familiar with. And basically, the crater deficits and the presence of the elephant hide terrain suggest effective downslope movement of regolith material. And this also, interestingly, of course, suggests weak physical mechanical regolith properties. So this is kind of important when we're planning astronaut traverses and rover traverses, and even Lunar like robotic exploration traverses. So next, please. So we examined this in much more detail. We looked at the downslope movement examples, and you can see here 3 craters that are potentially filled on the upslope side, shown the same in the top and the bottom, but just noted it with arrows showing the infilling there. So it's really going on, but we do not understand the origin of the elephant hide terrain. A simple downslope diffusive degradation process is probably not applicable. It doesn't seem to fit. Maybe it's related to seismic shaking, things like this. We don't really understand that. For more information on that, see Kreslowski et al. Abstract in 2021 and 2021 LPSC. But I'm not going to dwell on that, but we just still don't understand that. So that should be one of the goals here, is to try to understand the nature of the elephant hide terrain. Next, please. Now, when we take a look at this. Of course, we did the traditional geological mapping. We used all the LRO and other orbital data to map the properties of a 200 by 200 area around kilometer area around Mons Malapert. And then we formulated a stratigraphic sequence for the relative unit ages, and then essentially compile frequency distributions to get absolute model ages. Next, please. And so we have the geological map here. It's nested in the one I talked about yesterday, shown on the left. And you can see the average age of the whole surface is pretty old. And the next slide shows you then what we were trying to do, which is analyze human and robotic trafficability, given that we'd like to put the power station on top, probably the outpost and a base there, and then go south to get to, in fact, the potential water resources. Next, please. So what do we have that everybody needs to pay attention to from Lunicod and the Apollo LRV data? The Lunicod was two missions, incredibly interesting and quite sophisticated. They had a sophisticated soil mechanics sensors. They had targeted trafficability images, as you can see on the right. You can see it's moving back and forth, has moved back and forth in this image. And if you see that line in the middle, that is a soil mechanics prop experiment, which in fact isn't just the wheels we're looking at here and looking at the deformation of the regolith from that, but it's also actual measurements that were made by this instrument, the soil mechanics instrument, on a moving bearing strength of the soil, et cetera. So this is really important data. Next, please. And of course, we have the Apollo data, Apollo 15, 16, and 17. Jack Schmidt can tell you in detail how that worked on Apollo 17 because they moved up and down some significant slopes there, Station 6, et cetera. There were detailed soil mechanics experiments on all of these missions as well. And we had targeted trafficability images, as you can see on the left there. This is an Apollo 15 image of the rover tracks up the side of the Hadley Delta Massif, et cetera. And astronaut descriptions of walking and roving trafficability. Jack just described that, a little bit about how to move around on the surface, but the most effective ways were pay attention to those debriefings. They're really critical, not just the quantitative briefings, but the astronaut personal debriefings as well. Next, please. So we also have data from the field, okay? So there were tons of field tests for the Lunicod rover, okay, which Mikhail Malakov participated in, and shown on the left are two different types. The upper image is a image of that prop instrument getting soil mechanics, bearing strength, et cetera. And this is in volcanic ash in Kamchatka. And the same for this one, going up and down slopes and trying to assess the trafficability in that context. So on the right, you can see the summary that's listed in this paper, and the references are in the paper as well. On Lunicod, on the moon and the Earth, okay, from Malakov et al. 2008. And you can see here, this is not a linear slope. It's not a flat slope. Let's put it that way. So we're looking at slip ratio, the amount of slip as a function of angle, okay, the ratio of, okay, on flat, not much, but on steeper slopes, there's a lot of slip with slope degrees on the lower axis. So, basically below about 8 degrees slope, we're kind of okay, not too much slip, but there is some, and it's a nonlinear plot here. It quickly goes up, and you can see in all of the data, and particularly the Apollo data, it was pretty slippery on the steep slopes. Dave Scott on Apollo 15 and Jim Irwin, there were real problems on the Hadley Delta stops. Just simply the rover started to slide downhill in part, but also trafficability was really, really modified by that. And there's some good advice in the debriefing books on how you would convert that into walking around, doing stations, walking traverses, and also rover traverses. So, we really need to pay attention to these steep slopes here. And anything above like 8 degrees is going to be something to reckon with. We really have to plan in. And obviously Artemis 1, cancel that, Artemis 3 is going to really be able to tell us what the trafficability is going to be. And it's certainly going to be in real time, okay, because we don't have good data for the elephant hide terrain, et cetera. And the steeper slopes, we have to extrapolate from the Apollo and the Lunicod data. Next, please.
2 minutes.
So, in summary, going back to Malapert, slope trafficability data show access routes are really kind of limited that are less than about 10 degrees, okay? So the arrow that's pointing there to the left is what we recommended about how to traverse up and down the slope because it goes along the spine of the ridge and maintains relatively shallower slopes to get to the top. But that's not, that's a traverse, okay? So anything that's considering going back to the two craters in the south to harvest water, et cetera, is going to have to deal with this to get back to the base, or if the base has decided to put off the site and run wires to the energy, the solar energy, then we're going to have to traverse that to as well. So all of these things need to be considered in, and I really encourage you to take a look at these data, this paper, and factor these into your thinking. Next, please. So, in summary, please pay attention to the Lunicod and the Apollo data. It's really important, and all the debriefings, et cetera. Jack can fill you in on that. Really important. I just want to close by saying our team is now looking at Apollo 15 500-day design reference mission, in which we're looking at essentially. Somebody asked me years ago, what will we do for a 2 year? You want to go to Mars for one opportunity, or do you want to go for two opportunities and stay? And of course, well, yeah, of course, we want to stay. We don't want to do 40 days because you can't even get out of the spacecraft probably. But what's a 500-day mission look like? So we took the Apollo 15 site and said we want to do a design reference mission around something we know something about from the Apollo 15 mission results, but extrapolating out with a rover and human capability to a much longer distance, 500 days. So we're using these Lunicod and Apollo data on trafficability to apply to this 500-day mission to see what we can actually do in going up these slopes to a place we've already been. So I'll keep you posted on that, and I hope you find some of this information useful. Thank you very much.